When you woke up today, you likely touched a dozen materials before even leaving the bedroom. The cotton sheets, the wood of the bed frame, and the breakfast on your table all share one specific invisible ingredient: carbon. Even though it makes up only 0.02% of the Earth's crust, carbon is responsible for millions of different chemical compounds. It is responsible for more types of materials than every other element on the periodic table combined. Look at the structure of this uncut diamond. Because its atoms are locked together, it is one of the hardest, most rigid materials in nature. Now compare that stone to these piles of raw cotton. It is incredibly soft and flexible, yet it is also built from carbon. This versatility is what allows carbon to act as the primary structural frame for the vast majority of the objects we interact with every day. To see how it builds so much, we have to look past the microscopic tissue and down into the atomic level. Every atom here is playing by one universal rule. They all want exactly 8 electrons in their outer shell to become stable. Many atoms forcefully steal an electron from a neighbor or give one away to reach 8. They gain an electrical charge and snap together magnetically, called ionic bonding. But ripping electrons away takes massive energy, limiting how large these chemical pairings can grow. While this method works for simple things like table salt, it is too draining and chaotic to build the complex, massive structures required to create life. Here is a single carbon atom. It sits exactly in the middle of the chemical pack, with only 4 electrons in its outer ring. That leaves 4 obvious empty slots. Carbon is in a difficult position. Stealing 4 whole electrons from neighbors or trying to push its own away would require an impossible amount of energy. Instead of struggling to steal or give away electrons, carbon finds a more stable path. It simply holds hands to share its electrons with other atoms. This peaceful sharing is called a covalent bond. Because carbon has those 4 empty slots, it can hold 4 different hands at the same time. This simple geometry is what allows it to build such complex, stable shapes. Look at the bright blue flame under this cooking pot. That is methane, a simple molecule of 1 carbon atom holding hands with 4 hydrogens. By sharing its electrons this way, carbon forms stable partnerships without the high-energy drama of stealing. It is a reliable, steady way to build matter. Carbon's true strength comes from its willingness to bond with its own kind. 1 carbon atom can link directly to another. As you can see in this animation, carbon atoms act like microscopic Lego bricks. They can lock together to create long, straight chains. These chains can also flex. Watch as this straight line loops back on itself to form a stable 6-sided ring. These rings and chains can snap together to branch out into massive, complex 3-dimensional webs. This ability to chain together endlessly means carbon can build its own custom scaffolding for almost any shape nature needs. Because these chains can be shaped in so many ways, carbon is responsible for more types of compounds than every other element put together. Whether a material is a floating gas, a flowing liquid, or a hard solid depends almost entirely on the length of these carbon chains. Very short chains, like methane, are incredibly light. They are so small that they float through the air as invisible gases at room temperature. As you add more carbon atoms, the chains become heavier. They turn into liquids that flow smoothly, like the cooking oils in your kitchen or the gasoline in a car. If you keep adding atoms to create super long chains, they become dense and tangled. These form tough, solid materials, like the fibers in your clothes or the plastics in your home. By simply adding more carbon atoms to a chain, a substance can go from a weightless, invisible gas to a solid object you can actually hold in your hand. You can see this chain-building property in action every time you wash your hands. Since oil and water usually repel each other, how does soap help water wash away oily dirt? This animation shows a single soap molecule. It is a long carbon chain with 2 very different ends, a water-loving head on one side and a jagged, oil-loving tail on the other. Watch as the jagged carbon tail embeds itself into that brown blob of oily dirt. The tail anchors itself in the oil, leaving the head pointing outward. As more soap molecules swarm the dirt, they form a protective sphere. All the tails point securely inward at the oil, while the heads point out toward the surrounding water. Because those outward-facing heads love water, they act like microscopic tow trucks. When the water flows by, it grabs the heads and sweeps the entire trapped dirt package cleanly down the drain. The next time you wash your hands or eat a meal, you are experiencing the work of carbon, steadily sharing electrons and building the physical world around you.